This is 6.1, and it's called Systems of Equations. Systems of equations. Here's some vocab terms. System of equations is when you are graphing more than one equation on the same graph. So this right here is my graph. A system has like 2 lines graphed on it. Just like, if you looked at the map of a city from above, like an aerial view, you could see there's a system of roads. There's tons of roads intersecting, or some of them don't intersect and they run parallel to each other. There's systems. It's a road system.
Would it still be parallel if they never touched, but like one would like this?
Technically, it wouldn't be an equation because it's graphed out naturally. Oh, in a road? Yeah. Mm-hmm. Yep. Yeah. Yep. I think, yeah, because they don't touch. Yeah. Consistent is a new vocab word I'm going to teach you. Consistent just means that it has a solution. Consistent means that there is a solution. A solution exists. Now, there's consistent independent and consistent dependent. This is why you have your cheat sheet. They're easy to mix up. Consistent independent has one solution. If you think of an independent person, they like to do things by themselves. One person by themselves in their room, independent, on their own. Independence isn't a bad thing. But if you're overly independent, that is a bad thing, because people are social creatures, and they are, like, when you look at ecosystems, some pack animals who are by themselves, independent, are going to die because they're meant to be part of the pack. And if you don't have that social interaction, you're not going to thrive. Same thing for humans. It's like babies, if you leave them alone, it's called failure to thrive. They'll die if they're by themselves, because humans are designed to be, you're born into a family, you're designed to be with other people. It's interesting. Consistent dependent has infinitely many solutions. So independent has exactly one solution. Dependent has infinitely many solutions. I'm giving you lots of vocab right now. We'll use it in a minute. The opposite of consistent would be inconsistent. Oh, where's my red? Inconsistent has how many solutions? No solutions. 0. Inconsistent.
If we were to, you say inconsistent, we write no solution or your hours.
I would take it either way. Either way. So I'm going to show you all these things kind of in a chart here all put together. I want to show you a picture first. So in these 3 graphs, we're going to draw a picture of the 3 types. 3 types of systems. So one of the examples that you did with your pencils was you had one pencil looked like something like this, and one pencil looked something like this, or any combination thereof. How many times do these graphs intersect? Once. That right there is the solution. How many solutions does this graph have? 1. So number of solutions, this has 1 solution. According to our terminology, we're going to call this consistent because it has a solution, and independent because it just has 1 solution. For type, I can't think of what word I'm trying to think there. Consistent, independent, type. We'll come back to it. Maybe there's a word I'm just forgetting. No, they're not. They don't have to be perpendicular at all. They don't have to be perpendicular. They just have to cross. Perpendicular is the same as any kind of line. Good point. This graph right here. So we had one solution. What's another type where we had? Okay, we could do our parallel lines next. Yes, if I have one. That's okay. How many solutions does this one have? No solution.
What would your right equation of type would it just be?
I'm going to check back at my old notes. I don't remember. The terminology here is inconsistent. There are no solutions. And what's the last one we had? What was it? Yeah, when they're one straight line. So I want you to pause in your writing for just a second and look up here because I'm going to show you this, but you can't see it though when you're writing. So it's like you have one graph like this. So here's my first line. And then it's like you take another graph, a different quote-unquote equation, and it graphs it on top of that same line. How many graphs are there? 2, but it looks like there's 1. This is what you call, this has infinitely many solutions. Sometimes we abbreviate them IMS. We say that it's consistent, dependent, because they depend on each other. And the solutions are every single spot on this graph. There's infinitely many dots. Those are all solutions right here. Every single one of these infinitely many dots.
Do we have to write consistent, or can we just write typing?
You have to write both.
But what about the independent one?
You have to write both the words. You need both the words.
Do we have to write all the dots?
No. This is your own note, so whatever you gotta know. But I'm saying, but when you see this in the words, it'll always show you both of them. Okay, we'll skip the type for now. It might come back to me. And then for no solution, like they're not intersecting ever, so there's no solution here because there is no solution. There's no overlapping points. So an overlapping point is a solution. That's a big point of idea today. All right. If you got colors, now's a good time to get your colors out because we got a lot going on this graph right here. On your homework, it's going to ask you to identify what type of system this is or how many solutions it has. So if I have these two lines, I'm going to pick 2 colors. I'm going to do yellow and green first. My dad would be happy. John Deere. He loves John Deere. Yellow and green. This is just to help me. It's fine if you don't have colors. You'll be fine. So x minus 1, where on this big mess of, this is a system. There's lots of roads on here, lots of equations. Where on this system do you see the equation y equals x minus 1? You see this little speech bubble guy? See which one it's pointing to? It's pointing to this line. So I'm going to highlight that whole line as yellow. Then I got to find my green one, y equals negative x plus 1, right here. So how many times do the yellow and the green line intersect? 1 time. So I would say this has how many solutions? One solution. Sometimes on the homework it's going to ask you how many solutions, and then it'll say name the solution. Well, what's the name of the point where they intersect?
0, 1, or 1, 0.
1, 0. Yep. 1, 0. Sometimes, though, it's going to say, like, give me some words to tell me what this means. So this would be the number of solutions. But sometimes that's not the question they're asking. Sometimes they're asking, what's the name of this system? What would we call this? This is a consistent independent. So we would say consistent independent. I think for your first set of homework, you only have to write consistent independent. I'm showing you both, but just follow the directions. Okay, let's try number 2. Find on your graph x minus y equals -4. Where is that? I'm going to make that guy orange.
Please receive the center option. At this time, all sophomores going.
There's a field trip for sophomores today. So here's x minus y equals -4. I'm going to make that one orange. And this equation y equals x plus 4, I'll make that blue. Where's that one? They're pointing to the same line.
Please receive the center option. At this time, all sophomores going on the field trip should be released to the front lobby. Thank you.
So what type of system is this? If they're the same line, what's our terminology? What's that type of system?
Consistent dependent.
This is consistent dependent.
So we have an extra line.
How many solutions does it have? Infinitely many. So if it was asking for the number of solutions, you could just say IMS. Okay, let's try number 3. I got pink and purple. Oh, but I already made this one orange or blue. So, well, we'll just go pink. Y equals x plus 4. So that's this equation right here. And this equation, 2x minus 2y equals 2. Oh, that's this one right here. What about those two graphs? My 2 purple ones. Or my pink and purple. What type is that? They're parallel, and what type is that? I'm looking for the word inconsistent. I'm looking for the terminology. Inconsistent. How many solutions does it have? Parallel lines. How many times do they cross? Never. So there's no solution. Okay, last type. Y equals 2x minus 3. I'll make that one pink. 2x minus 3, that one on my graph is right here. The only line I haven't used yet. And the equation 2x minus 2y equals 2. Whoops, that's this one right here. What type of system is that one? Those two lines. How many times do they cross? Once? So what's the terminology I'm using here? Consistent, independent. Good job. I remembered the type. So type, these are just intersecting lines. Inconsistent means they will always be parallel lines, or lines that never intersect. This type, though, is the same line. Okay, so the first part of your homework is tell me if it's inconsistent or consistent, independent, consistent, dependent, or inconsistent. Think you can handle that? Looking at a picture just like that. All right, flip it over. On the back. This is where we're using our chart. Remember I said that there are different methods for solving. Methods for solving systems of equations. This is the first method. I'm about to show you the first method. Are you ready for it? Well, get ready. Solve by graphing. Solve by graphing. Man, we gotta graph some graphs. We'll do the first one by hand just for old time's sake. So if I was going to graph this equation, y equals 2x plus 3, what's my starting point?
3.
3. And what's the slope? Up 2 over 1. Up 2 over 1. Up 2 over 1. I could connect those dots. Man, what do I do about that bottom equation, though? Find your intercepts, or you could solve for y. In this situation, I'm going to solve it for y because I'm going to show you how to do this on the calculator, and to do it in the calculator, you have to solve for y. So we need to get y by itself. What do I do first? Minus 8x. So I get negative 4y equals negative 8x minus 12. Divide by negative 4, divide by negative 4, divide by negative 4. So I get y equals 2x plus 3. What do you notice? It's the same line. Whoa! So you could tell me how many solutions does this graph have? So you got to pay attention to what the question's asking. If it says how many solutions, yeah, you would say IMS, infinitely many. If it said what type, what would you say? You wouldn't say same line. The terminology. So you would say consistent, dependent. I'm sorry about the confusion on the type. I should have switched those columns in the table. The instructions will be clear. You'll know what it's asking. Okay, well, I don't know about you guys, but I don't really want to graph all these by hand. I mean, does anybody really want to graph these by hand? Anybody? Anybody? Bueller? Yes? You can graph them by hand if you want to. But the problem is, sometimes you're going to get decimal answers and it won't always work. So, I'm going to teach you how to do this on the calculator. So, let's skip B for now. Let's move down to C. And I'm going to give you some calculator steps here. So if you don't have a calculator, get one. First step, we're going to press the y equals button. We will in a minute. Y equals,
Time all sophomores should be in the lobby to go on the field trip. Thanks.
So
And-
I'm going upgrade. I'm gonna just.
yeah, okay, yeah. Y equals x plus 3. That's my first one. Then you move your arrow down. And it's y equals 6. Is that okay? Yeah, you're just going to put a 6 there. Because see how we got a y equals and a y equals? Here's my two equations. Then what do you push? Graph! Oh dear. I hope your graph doesn't look like mine. Anybody having trouble? Mine's got some statistics going on. Sorry about that. Anybody having trouble with your calculator? Should look like this. If it doesn't, raise your hand. Okay. Anybody else got anything weird on their calculator?
No.
Anybody? Okay, we got, what type of system is this? Consistent, independent. Good job. Consistent, independent. How many solutions does this have? 1. Your calculator will tell you the point where they intersect.
Do you have to graph it even?
Well, yeah, you have to put it in there, and then I'm about to show you the steps to find where they intersect.
No, I mean, you have to put it on the graph of the
No. Well, I don't know. I haven't decided. Okay, so here we go with the steps. We're going to press the second button. Second. It's going to be calc, but it's really the trace button. So second calc. Stop talking, guys. Second calc. Type this in, please. Second calc. It's trace. The trace button. See how it says calc in yellow behind it or blue? Yeah. I'll say second calc a lot. Second trace. And then we need to go to, which one do you think would tell you where they intersect?
5.
Number 5, where it says intersect. So if we go down to 5, intersect. Okay, now look up here. It looks like nothing happened. They didn't tell you where you intersect. But you have to tell it to tell you. See how it's asking you a question right here? What does it say? First curve, question mark. Curve is like a graph. You would press enter to say like, oh yeah, this dot's on my first curve right here. And now it says what? Second curve, question mark. So you push enter to say like, yeah, that's the second one. Now it says, guess, question mark. You're like, yeah, okay, go ahead and guess. Bam! Now what does it say?
X equals 3, Y equals.
What does it say? Intersection. That's how you know you did it right.
So cool.
So cool. So the intersection point is the point 3, 6. So right here, this has one solution, and it's the point 3, 6. So you will have one on your test where you're going to have to graph it by hand. I'm not spending a lot of time on that because I feel like we got it. But just make sure you got it. Okay? So for the steps, first we pressed y equals, and we typed in the equation. Both equations. After you graph them, we pressed second, what was the button again? Trace. Second trace or second calc. And then we went to number 5, where it said intersection. Or did it just say intersect? Intersect, yep. And then we pushed enter, enter, enter. 3 times. And then it gave us the points. Whew, let's try that again. What happens if they give you 2 examples in standard form? Oh dear. They have to be in y equals. It won't work if they're not. So we'll change this first one into standard form. Negative 4x plus y equals 11. How do you get y by itself? Add 4x to both sides. So y equals 4x plus 11. That was a good one. So that's one new equation. Let's do this next one. We're going to get it into y equals. So 12x minus 3y equals negative 33. How do you get y by itself? Minus 12x first, yep. And then we divide by negative 3. So y equals 4x plus 11. Wow, these are going to be the same line too. Do you really have to graph that on your calculator? No. It's going to look something kind of obnoxiously huge like this. How many solutions does it have? Infinitely many solutions, IMS. You're not saying all real numbers. You're saying IMS, infinitely many solutions. That's how many solutions there are. Okay, let's do example B. Sorry to jump around on you. Let's solve this one for y. I'm going to do it up above. X minus 2y equals 4. How do you get y by itself? Minus x. How do you get y by itself? Divide everybody by negative 2. So y equals negative x over negative 2 plus 4 over negative 2. You could leave it just like that. Could you simplify it? Yeah. Do you have to? No. It would be x over 2 if you wanted to simplify, minus 2. Let's convert this one to y equals. Minus x on both sides. So negative 2y equals negative x minus 2. Divide by negative 2. So y is negative x over negative 2. Yeah, that's where I always just get confused. Plus negative 2 over negative 2. That simplifies to be y equals x over 2 plus 1. So I'll use my two simplified equations here, this one and this one. Did I lose you in the math? Anybody stuck on what I did there? Now when we graph it, we're press y equals, we got to clear out our graphs. Clear them out. Practice at least the graphing with me, even if you are still writing down the math. You can pause on that for just a second. Get yourself to the y equals, clear out your screen. Y equals x divided by 2 minus 2. That's the first one. Down here, this would be x divided by 2 plus 1. Graph it. There's one. There's the other one. Wow. Huh. I wonder if these lines are going to intersect. They're parallel. Now watch what happens. Let's just practice our steps. So we type them in. I get this all the time, so don't be this person because I'm about to show you what happens. Look up here. So you have second trace, number 5, and then we press enter, 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 right? enter, enter, enter. And then I get, Miss Wagner, my calculator's broken. It's broken. It's not working. It's broken. The calculator it's broken. And I don't know if you can fix it. It's broken. It's broken. That's what I get all day long. It's not broken. It's telling you what's going on here. What does it say? No sign change. Well, why would it say error? You asked it to tell you an intersection. Do these points have an intersection? No. It doesn't know how to do that. There is no intersection. So if you get error, it's not broken. It's no solution. So this would be no solution because they're two parallel lines. They had the same slope also. That's a quick way to tell. Parallel lines have the same slope. Okay, last example, then we're done. You guys are doing great. Jane, she likes running. I like running too. She ran 5 miles yesterday, and she plans to run 3 miles per day. Austin, he also likes running, ran 2 miles yesterday, and plans to run 4 miles per day. Oh, sorry, I didn't change the names down here. Jane and Austin will have predict the day when Jane and Austin would have run the same number of miles. Wow, this sounds like a system of inequalities or equalities if I ever heard one. So let's write an equation for Jane. Jane ran how many miles yesterday? 5. Plus, she's going to run 3 miles per day. Whenever you see that word per, that's a good sign that it's going to be an X. That's going to represent how many miles she runs in X number of days. The total miles that she ran that week or something. A lot of runners check how many miles they run per week. And you should build your mileage. If you're training for a marathon, you build your mileage about a month. Well, on a weekly basis, you increase your mileage about 10 miles, 5 to 10 miles a week. Your long runs, you increase by 1 mile per week, typically. Austin is going to have a similar situation. So he ran how many miles yesterday? 2. Plus, he's going to run 4 miles per day. Predict the day when they would have run the same number of miles. Guess what? We can use the calculator to do this for us. Y equals, clear these babies out. 5 plus 3x. 2 plus 4x. Graph them. There's 1. That's Jane. That's Austin. Let's see where they intersect. What do I push? Perfect. And they say the intersection is 3:14, but we have to interpret what that means. This is X and Y, right? Not quite. Okay, I'll help you in a minute. What does the X represent in this situation? X represents days or miles? Days. Y represents miles. So what does 3:14, what does that point, that ordered pair tell you?
3 days.
3 days,
14 miles.
14 miles. So on the third day, both of them ran 14 miles total. 3 days, 14 miles. You with me? So predict the day, how many days is it going to take? 3 days. Your answer is 3 days, not 3:14. Okay? So there's a lot of higher order thinking. This is like complex problem solving here. This is where math and honors starts to get tricky because it's not just like, oh, I can follow all Miss Wagner's steps. It's I can follow all Miss Wagner's steps and I can think about it and interpret it. This is where math starts to get hard. You guys are up for it though.